I'm Professor Sooyoung from Chung-Ang University, and what I'd like to present is about physical AI and what is focused on manufacturing. So the term physical AI has emerged as a promising concept interacting with the physical world, but despite its increasing popularity, it seems that the definition of physical AI is still ambiguous. So I like to share my perspective so that we can actually visualize better understanding of physical AI and with the context of manufacturing applications. So first, I would like to briefly go over several phases of AI. So it goes all the way from perception AI, generative AI, agentic AI to physical AI. So it started with something perception, which focused on recognizing patterns from data, such as for detection tasks. And it was followed by generative AI, such as ChatGPT, where the models are trained to approximate high-level data distributions to generate something. And it was expanded to agentic systems to autonomously execute a task. And finally, we are seeing a shift toward physical intelligence that make decisions in real-world physical space. So many people describe that it is a transition from digital to physical problem. But one thing that is ambiguous is that in our field, manufacturing, engineering, or industrial applications, we always deal with physical systems, right? And we've been applying AI method to those systems for many years. So that raises a question that what is the difference of physical AI compared with AI deployed in physical systems? So let's take a look at example. So this is simply a random case found in Google. And as you can see in this figure, one company built an inspection robotic system and it combines a bit of AI method to find like defects automatically. So it is clearly AI-based decision making and it also operates in a physical space, right? So can we call this physical AI? Personally, I like to say yes, but technically, it is somewhat different what many people refer to as physical AI. So the main reason is that even though the system operates in a physical space, this system mainly serves as perception platform, and it seems that it does not autonomously reason about physical actions. So under this motivation, I like to discuss how we can clearly define physical AI. So this is my own version of working definition of physical AI. And in this definition, I believe the key part here is to enable physical systems to sense, reason, and act. So it should form a tightly coupled and continuously influence of sensing, reasoning, and acting, like perceive the environment and understand the situation and make decisions with physical actions. And under this umbrella, one of the representative approach is vision, language, action framework. So sensing with visual observations and reasoning from prompt instructions and acting by generating physical action states. So once this model is trained, you can see that the physical system can generate appropriate actions autonomously according to different situations. But thing is, we need a bunch of data sets. So if you keep track of physical AI studies, you might know that the majority of studies heavily rely on purely data-driven methods. So that means we need to collect every data, as many as possible for sensing and actionable physical scenarios. But even for a simple pick and place, we might need to repeat the same operation hundreds of times to collect training data sets, which is impractical to obtain large-scale action data sets. So this raises a question that how we can effectively incorporate problem-specific characteristics while mitigating the data scaling limitations. So one example, we focused on assembly problem. So as an interesting benchmark, we consider the 10-gram example, where the physical system is required to assemble different target shapes using a set of geometry pieces. So this problem requires collecting lots of high-quality demonstrations of the assembly process, and this is very expensive process. But we formulated our problem with different perspectives that assembly and disassembly are inverse process, but they are not equally difficult. So assembly requires precise planning and manipulation, but disassembly is much easier if we simply take it apart without any particular strategy. So we came up with interesting idea that leverage the disassembly process and exploit the inverse relationship. So based on this idea, we proposed our own VLA model called D2A VLA, which is trained to learn explicit assembly manipulation trajectories, inversely mapping from implicit distributions of disassembly demonstrations. And as you can see, according to different language instructions, our model successfully generalizes to a variety of autonomous assembly tasks. Going forward, we wanted to extend our idea to mechanical assembly. However, unlike the 10-gram example, mere mechanical assembly is much more challenging. So the reason is that during assembly or disassembly, the parts are not independent, right? And they have kind of dependencies, meaning that they cannot be assembled or disassembled in an arbitrary order. So we propose a learnable graph representation that captures the relationship between the parts. And we developed a novel VLA model that uses this relationship as a graph chain of thought. And the results show that our proposed model is able to perform kind of complex mechanical assembly autonomously. So far, I've shown working definition of physical AI based on sensing, reasoning, and acting, and along with some of our studies with problem-specific knowledge integration. However, from aspects of physical AI for manufacturing, I believe that this framework needs to be extended. The first one is adapt. So the manufacturing systems often operate in dynamic and uncertain conditions, so the physical AI needs adaptation, such as for changing environment. And the second capability is collaborate. There exist multiple physical systems working together, so we should care how embodiments collaborate rather than isolate. As I mentioned, manufacturing environments involve various sources of uncertainty. So one good example is acoustic environments. So the acoustic data can contain a lot of rich information, but they are also highly sensitive to environmental changes, such as background noise and variations in operating conditions. To address this challenge, we proposed uncertainty-aware VLA framework, where the generated actions can continuously evolve based on reliability and uncertainty. And as shown in the results, under diverse environmental disturbances, the proposed model gradually converges to more accurate and reliable actions rather than producing a fixed action sequence. For collaborate, first we focused on human-machine collaboration. So in this study, we aim to enable human-in-the-loop decision-making where physical systems and humans coordinate and refine decisions together. To achieve this, we developed a signal-specialized large language model that translates complex mechanical signals into natural language representation that humans can easily understand for more effective collaboration. We also explored machine-machine collaboration method. As I said, in real applications, multiple physical systems working together for common objectives. To do this, we developed VLA to VLA transfer mechanism for collaborated embodied agents. And as you can see, different physical agents communicate each other to refine their shared task. I think it's meaningful because it represents an important step toward agentic physical AI, where multiple assets can coordinate their actions simultaneously in complex environments. And the last one I'd like to discuss is about physicality for physical AI. So if we think about literal meaning of physical, it has three aspects: embodiment, tangibility, as well as physical laws. But many concurrent approaches simply lie somewhere between embodiment and tangibility. So I believe that physical AI deserves much greater attention for physics itself. Suppose we have chip placement problem. With a sufficient training of VLA model, physical system may learn how to place a chip accurately. But what if the model can learn the underlying physics of the placement process, like thermal behavior, electrical performance, or any other physical behavior of the system? In other words, physics-aware physical AI can assign much more engineering semantics to its actions, rather than treating actions as merely a sequence of motions. So where physical AI meets physics harnessed engineering semantics, we define this direction as extended physical AI. Not limited to the previous example, we are expanding a range of studies under this extended physical AI. For example, intelligent robotic grasping that understands physical characteristics, and industrial applications like rotary process control with physics-guided virtual sensing, targeted particle evolution in spray coating process, and additive manufacturing optimization guided by differential physics. So I hope this perspective inspires more vibrant studies in this exciting area. Right, that's all for today's presentation, and thank you for your attention.